Next up, we have Forrest Ward of Firefly Aerospace presenting on an automatic engine trim capability for launch vehicles. Forrest, it's all yours.
All right, thank you, Brandon. And thank you to the Flight Software Workshop for inviting me to speak today. My name is Forrest Ward. I'm the Guidance, Navigation, and Control Manager at Firefly Aerospace. Firefly Aerospace is an end-to-end launch transportation company. Most of our time and effort and hardware development has been spent to date on the launch services part of that business, notably our Alpha launch vehicle. We had our maiden launch of that vehicle last September. We experienced some off-nominal behavior during that flight, and my talk here today is going to talk about how the Alpha flight software, in particular the Alpha guidance, navigation, and control software, responded to those off-nominal conditions and prevented a more serious outcome and was able to prolong the flight in order to gather valuable flight data that we're going to use to improve our chances of success for future flights. Next slide, please. So our maiden flight occurred on September 2nd, 2021. There's a picture there to the right of our beautiful liftoff. That flight was from Vandenberg Space Force Base, Space Launch Complex 2. We're honored to be flying from the old Delta II pad with a lot of history. 13 seconds after liftoff, we experienced a loss of thrust from one of our 4 first stage engines. An engine out scenario like this can hurt you as a GNC engineer in 2 ways. The first is an obvious one. Obviously, you from a velocity standpoint, you get a lot of extra delta V losses due to the decrease in acceleration you get. You spend those precious early moments fighting gravity when you need to be accelerating. That's one way that an engine out situation hurts you. The second is from a controls perspective. If that engine that goes out is not centrally mounted, then you're going to have a thrust imbalance occur. And that's, as is the case with our aft section, we had a thrust imbalance from an opposing engine that needed to be contended with. The GNC system on Alpha was able to do that, keeping control of the vehicle for 2 minutes while the vehicle continued pitching down range. And again, making it up to supersonic speeds, allowing us to gather some valuable flight data. Next slide. So zooming out a little bit, I want to talk about the Alpha vehicle architecture, just for those that don't know, and talk about the relevant elements as it pertains to the GNC system. So as you can see in the cutout to the left, Alpha is a 2-stage bipropellant LOX-RP launch vehicle. The GNC algorithms run with the rest of the flight software on a single flight computer located on the 2nd stage. Also located on the 2nd stage are some important hardware for the input to the GNC system. So first, GPS antennas and receivers that provide the GNC system position and velocity throughout flight. Second, and importantly, the inertial measurement unit, the IMU, is located on the 2nd stage that provides high rate acceleration and rotational rate data to the GNC algorithms. On the 1st stage, we have a 2-axis rate gyro that we use to blend rate data with the IMU in order to filter out vehicle bending modes. So that's on the sensing side. On the control side, or the way that we control the vehicle's orientation, we use a combination of thrust vector control and reaction control system. On the 1st stage, we have 4 engines utilizing single axis TVC per engine. That is, each engine can only move in a single plane. We did that as a way to increase the simplicity of the aft end, the fluid section back there, as well as decrease the amount of dry mass we're carrying. And if you look at the math and you do the linear system of equations, you can see that for an array of 4 engines with 4 thrust vector control actuators mounted perpendicularly, you're able to achieve an arbitrary torque direction in order to steer the vehicle or reject perturbation torques. And that's just what the GNC system does during 1st stage flight. On the 2nd stage, the centrally mounted Lightning engine, we actuate in pitch and yaw during flight and handle roll using the reaction control system. During periods of coast, we handle roll, pitch, and yaw using the reaction control system. So those are the important elements on Alpha of the GNC system. Also notable in this cross section, you can see the ribbed elements in the vehicle's tanks. You can see that the second stage smaller tanks have a few. The first stage tanks have more, but each tank has some. Those are slosh baffles that we use to dampen out the effect of the liquid propellant sloshing around in the tanks as we're flying. Slosh can have the same effect that any external torque like wind or an engine out can have on the vehicle, and that is to pull the vehicle off its desired trajectory. So another example of a perturbation torque that we can experience during flight. Next slide. So zooming in a little bit on the Alpha GNC system. So the GNC application runs as part of a larger flight software suite of applications. And I think everyone on the call probably understands intuitively the purpose of a GNC system, that is to steer the vehicle. But specifically, how do we do that? We do that by splitting this problem up into 3 sub-problems, smaller problems. And those are, where am I? That's navigation. Where do I need to be going? That's represented by guidance. And how do I get there? Or what corrective actions do I need to take with my actuators in order to bring where I am into agreement with where I want to be? So that's the difference between those two we call error. So the role of the control algorithms is to reduce error. The graphic on the bottom left kind of illustrates how this is all kind of laid out with some of the elements I described on the previous slide shown there. We got GPS and IMU serving as inputs to the navigation system running on the flight computer. And on the control system, we have outputs in the form of commands going to TVC actuators on the first stage and TVC actuators and RCS thrusters on the second stage. I included engine shutdown here because GNC as a flight software application is the software that has the information about where we are in relation to the orbit that we want to end up in. So on Alpha, GNC sends the flag to flight software telling flight software it's time to shut down the engine because we're in the right orbit. So how do Firefly GNC engineers do all this? We work pretty closely with the flight software proper team. We're under the same organizational umbrella. We sit next to each other. We hardware in the loop test with each other. We kind of consider ourselves flight software engineers. The flight software team might disagree with that while doing our code reviews, but we get a lot out of that kind of tight-knit relationship. I think it's served us really well to move fast without making a lot of mistakes. So what tools do we use to do our GNC work? I've often thought about adding an S onto the end of the acronym GNC for simulation, just due to the criticality that simulation plays in our day-to-day jobs. You really can't evaluate the performance of your GNC algorithms without a good simulation. So at Firefly, we use a combination of in-house developed and industry standard tools, and we make the decision between the two, when appropriate. Our highest fidelity simulation environment is in-house developed, and that's where we can kind of really get our hands deep into the code and create models that are very alpha specific that you can't get off the shelf, obviously. So shown at the top right is an a visualization of that 6 degree of freedom dynamic simulation. And that's really our primary analytic tool. It really gives us the predictive power to determine how the vehicle and our software is going to behave after liftoff. So we use that simulation environment for basically everything. Any change to software must pass a number of tests involving that simulation environment. We use that simulation environment for everything from running nominal scenarios, verifying payload performance, to calculating in Monte Carlo the probability of mission success for a given mission, all the way to an even bigger analysis where we're calculating the vehicle's launch availability or the chance that we'll be able to fly from a given location at a certain percentage of time. Next slide. Okay, so a little more detail on how the GNC system responds to these perturbation torques. We've programmed a proportional derivative controller into our software. It's pretty standard. And you can see at the simple cartoon at the bottom, starting at the left, you've got a rocket flying straight, doing everything it's supposed to do, and then gets hit with a perturbation torque, such as an engine going out. But that perturbation torque can really come from anywhere. I mentioned regardless of its source. That's possible because the IMU and the navigation solution are picking up pure vehicle kinematics. It senses that the vehicle is rotating. It doesn't know or care what's causing that rotation, and that difference in from where we are and where we need to be is picked up and sent to the control system as an error. So you can see ultimately the corrective action is taken on the right, that a rejecting torque is generated by rotating the TVC actuators properly, and not just to reject the torque, but also overcome the initial error that it caused. So if you were expecting from my talk a complex slide here describing a neural network and fault detection, you might be a little disappointed by the PD controller and a bad cartoon, but that's really the point I'm trying to make here, is that you can create a robust and adaptable software system right out of the gate just by following fundamental principles and writing code that's tried and true. Next slide. So going into a little more detail about our specific perturbation torque that we experienced during our flight. So the loss of thrust at 13 seconds in our flight was caused by a main valve on the R2 engine closing unexpectedly. The image on the bottom right is actually our CEO, Tom Marcusic, in an interview with vlogger Everyday Astronaut. They're standing next to a Flight 2 first stage engine. And what Tom is pointing to there is actually the exact electrical connection that caused this issue during Flight 1. I'd encourage everyone to check out that interview on YouTube. It's a very open and interesting interview that gives a lot of insight into Firefly. So as I kind of alluded to earlier, this engine out caused some perturbations in our rotational dynamics and translational dynamics, obviously. Rotational dynamics were kind of described on the last slide. The effect on translational dynamics are shown in this cartoon version of this graph here that shows the effect that an engine out has on your thrust to weight. So you lift off and you're seeing you're depleting mass, and you're seeing this parabolic increase in thrust to weight. You get an engine out, that you see a step reduction in your thrust to weight that you kind of have to claw back from over time as you deplete mass and reach the accelerations that you were at before the engine out. Next slide. So how specifically did thrust vector control commands respond to this engine out? To help with that, I've got an engine layout on the bottom left shown. This image is kind of looking from the aft of the first stage, looking forward. You can see the four engines there. R2, the one that went out, pictured at the bottom of the array in this view. The white arrows indicate the direction of motion allowable from the thrust vector control actuators per engine. So again, the single actuator design does limit us in that we're only able to move in this plane. So you can kind of, oh, and another thing is Firefly follows the convention of, we call rotation about the y-axis our pitch motion, and we call rotation about the z-axis yawing motion. So you can see engines R1 and 3 are our pitch engines. Engines R2 and R4 are our yaw engines. And all four engines can create a pure roll torque by moving clockwise or counterclockwise. So you can kind of envision the scenario here. You lose thrust from R2, and now R4 is left unbalanced about the y-axis. And what we saw in flight is, R4 can't even reject the torque that it's creating due to the limitation of its thrust vector control axis. So that disturbance gets picked up via the IMU and sent through the control system as an error in the vehicle's attitude. And what we see is the engines R1 and R3 point their thrust towards the out engine in order to stabilize the vehicle and return it back to its desired orientation. And we see that happening in telemetry. The graph to the bottom right is a simplified version of the telemetry we see, where shortly after liftoff, you're seeing small corrections about the null position. Once you see the engine out, R1 and R3 move quickly to rebalance the vehicle and compensate for the offset in thrust. And they kind of remain there for the rest of the flight. You can imagine, there's no free lunch here. So you're able to maintain control of the vehicle, which is good. That's your first priority. But now you've reached a new static trim where you're imparting a net force on the vehicle in the lateral direction. And you're also eating into your total control authority on one side. So if your engines have reached this new trim off of the null position, you don't have as much remaining control authority on that side as you did to begin with, to reject any additional perturbations like wind that you might encounter. Next slide. So we see all of that confirmed in telemetry. That was good to see, but we also see it confirmed in video evidence. So the pictures on the right were taken from video footage of our first flight. You can actually see on Firefly's YouTube channel. It's some exciting footage I'd also recommend you check out. But the top image is very satisfying to me as a GNC engineer and to the rest of the GNC team. That image is taken well after the engine out and the vehicle's corrected itself. It's continuing its pre-programmed downrange pitching trajectory. But you can see there's an engine out and it's still going up. And so was a really good example of a real life scenario where we're seeing the software that we've spent years working on, working in a unexpected stress test. The photos at the bottom show the aft end of the vehicle shortly before and just after our engine out. Shortly before, you're seeing the small corrections about null, mostly axial thrust. And shortly afterwards, in the video footage, you can see it's almost imperceptible, but you can see the correction in the pitch engines R1 and R3 as they move to direct their thrust towards the out engine. And the arrows shown near the CG are to illustrate the vector components that you're getting resulting from the new static trim. So most of your thrust is still axial, which is good. But due to the static trim, you've got a small amount that's actually pushing the vehicle laterally that you'll have to contend with. So the vehicle continued flying for 2 minutes. We reached supersonic velocity until we were unable to maintain control. But those 2 minutes were kind of gold for us in our ability to gather all kinds of data on the vehicle, propulsion, structures, avionics, fluids, and press systems that we'll be able to use and build on to validate models to improve our probability of success for future flights. Next slide. And that's all the content I have, and I'm happy to answer any questions.
All right, thank you, Forrest. We do have some time for questions. We have one already in, which is, how do you measure thrust from a single engine?
We do that on the ground. We don't do that during flight. We use a combination of load cells that measure that thrust, as well as parameters within the engine, and from a thermodynamic perspective, pressures and flow rates.
Okay. Give a few more minutes, see if any other questions filter in.
Sure.
Next question on the chat. Have you noticed that flex is an issue across the launch vehicle?
We did see evidence of flexing in our post-launch review. We saw that all of the expected flexural modes of the vehicle occurred where we thought they would. We saw some evidence of some other ones that were taking account of in future flights. But yeah, we're really happy that we put that gyro on the first stage for the first flight after the data we were seeing.
Okay. Let's see. The next question is, what is your software stack in GNC and how does it work with the rest of the flight software stack?
Yeah, I'm not sure how much detail I'll be able to provide on the exact stack. Maybe our director of software in the town hall tomorrow can answer that. But GNC in our design runs as a single VxWorks application in a suite of other applications that handle tank pressurization, telemetry, and so on. So in that sense, what I can say is the GNC application is equal to those other VxWorks applications and contains its own shared memory and inputs and outputs to vehicle sensors and actuators.
Okay. Give it another minute and see if any others come in.
Happy to answer any more on the Slack as well.
All right. Next question is, what was the most interesting behavior you found in the telemetry data that you did not expect, aside from the engine?
Oh, you took away the obvious answer. Let's see. We know some interesting data from the GPS late in flight. That was mostly when we started to lose control, which I guess is expected, but interesting behavior that shows us the limits of a useful lock of GPS later in flight that we'll be able to use and put into our simulations moving forward.
Okay. All right. Forrest, thank you so much for your time this afternoon.
Sure thing. Thank you, Brandon.